record, share screen. You are screen sharing. Jackpot. All right. So let's get to it. Basically, what I'm teaching you today goes perfectly with what we've been doing the last couple of days. And I'll give you 4 examples today. Your assignment will have 4 problems today, not a coincidence. And then the assignment tomorrow will be a collection of what we've talked about today and yesterday. And it'll probably have more like 7 or 8 problems or something like that. So anyways, today is the 4th. Today is 10-4, Captain. And today we are doing zeros with multiplicity. Tried to write that word in my bestest writing so that you can see the spelling. It's one of those words that really does just get spelled the way you think it should, right? No trickery there, multiplicity. And this actually came up on assignment number something, like maybe assignment 8. It was a do you remember the one where we had the zero? I think did we talk about this in the bounce root? Do you guys remember that? The zero that came up and touched the x-axis and then backed off. It didn't go through. We're going to focus on that kind of idea today. Anyways, that idea is called multiplicity. So when we go through and we factor these, we find the zeros, and a single zero can occur multiple times. It can occur 2 times, 3, 4. I think we'll see one today that's 5 times. And when that happens, we say that that zero has multiplicity. And how much multiplicity it has determines how it behaves. So that's the distinction. That's the goal for the day, is to get you to be, you should already be relatively adept at the factoring and the finding zeros, the talking about end behavior, figuring out positive, negative intervals. Like that ought to already be in place then before today. And then today we add in the new stuff, the weird ones, the zeros that do funny things. So got it? So I got 4 examples for you, and here is the first one. And it's nice that it's always nice when like we don't have the super awkward introduction. Like we've already been down this road. We know generally what to do. So we can just add on a little new layer of understanding today. So you look at that, and at first glance, you're like, been there, done that, right? What do we do first? Yeah, pull out that GCF, which is definitely a negative. And what else? We can get a 5, and we can get a pair of x's. So perfect GCF, negative 5x squared. And then the remaining polynomial is what? You got it. Yep, -6. Good job. Good teamwork there. Have each other's backs when we do stuff like that. Good job. And so then we're going to factor the white trinomial that's left over, and we're left with 3, well, actually 4, maybe arguably 5, all of our factors. So we have negative 5x squared, and then we have x minus 3 and x plus 2. Say, you can clearly see why we do a small unit on factoring before we press in, because it's nice to not have to stop every time we factor and talk about how'd you get that or how'd you get that. It's super nice. So now it's time to talk about the zeros. And remember, the entire sort of crux of all of this has been going back to the first day, that the idea is that we're trying to make the function's value equal 0. If I can make the graph's function value equal 0, then I am necessarily finding a point on the x-axis, and that's what I'm searching for. So if you see me occasionally write equals 0, that's just me reminding us that don't forget why we're doing this. It's an equation set equal to 0 that we solve by factoring. So this is an interesting sort of thing, and I don't think you'll struggle with this idea, but in this red box, there are 3 factors. One of them is negative 5, and the other 2 are x and x. And so when we think about like what 0 or what answer do we get out of the red box, you know this from our experience already, that the answer is, oh, 0, remember? Anytime a factor, a GCF, excuse me, has a variable in it, then we know it's going to provide us with an answer, right? However, you would of course notice in this case that it's not just negative 5x, it's negative 5xx. And so each of the x's inside of the x squared produces its own 0. So we say in a case like this, that this 0 has multiplicity of 2. And that's going to be our notation for multiplicity. I put just a little times 2 to show the reader of my work that I'm telling you that 0 is an answer, but it counts for 2. And if you want to know why that is, I can show you. I saw some nodding heads earlier when I did this, and so perhaps this will make you go, oh. If I take what's in the red box and I were to write it out, I'll use green over here off to the side. If I listed it out, the factors in the red box would be negative 5 times x, right? And so we know, of course, that negative 5 cannot produce anything because he does not have a variable. But we then have to understand that this x gives us a 0, and this x also gives us a 0, and that's where that multiplicity comes from, is that there's actually 2 of them there. Does that make sense at all? Okay, so let's talk about the first white set of parentheses then. What 0 do we get out of that? 3, and that's just a single normal multiplicity 1. So you don't need to specify multiplicity when it's 1, like we just assumed that. And then the last one is what? Good. Any issues so far? Okay. So today, throughout the next 20, 25 minutes, whatever, I'm going to try to give you the full sampler platter of the different ways that zeros can behave. So this will be our first kind of glimpse, and I thought it would be nice because you've seen this behavior before. So first, let's talk axes. So when I think about making my graph, I want to kind of think about not wasting too much real estate. And so I know my furthest left 0 is negative 2. And I know that my furthest right 0 is positive 3. So perhaps I make my axes look like that, a little longer to the right. If you're not worried about things like that, then that's fine. Good, good. So now I'm going to go through and I'm going to place my zeros. And after that, we'll go backwards and we'll have our conversation about end behavior. Because remember, the zeros on their own are not enough to establish structure. We need the end behavior to tell us things. Well, you know what I mean. So let's place our zeros. I got a 0 over here at negative 2. And I'm just freestyling, man. Like, I'm not worried about making it perfect. And then I got a 0 here at, well, 0. And then I've got my final 0 over here at 3. So I'll just kind of guesstimate where 3 might be, like up there. At the beginning of this problem, excuse me, if you look back, we started out with a negative 5 and an x to the 4th, right? So those two factors put together, they together come as a team and give us our end behavior. So what does the 4, generally speaking, tell us? It's either down, down, or up, up, right? So just on his own, the even exponent tells us that the arms will not do different things. They'll be the same. And then, yeah, Emma, this negative 5 in the front specifies then that they're both down, right? So that information is massive because then when I go to construct my graph, I understand now that the graph has no choice but to end down over here and to end down over here. And you might have to modify that later. It doesn't, and again, we're not going for artistic mastery here, but just to have those little arrows drawn is really what the brain needs to go. Yeah, I see. So what is the graph going to do at negative 2? It's just going to cross. So like this 0, negative 2, because there's only one of him, right? He's a single root. And so there's absolutely no hijinks going on at negative 2. So that's just a crossing point like we're used to. And then it's going to bend back down. Do you by chance remember? Now this is our next one. I'm going to make it green for you. This is significant. What's going to happen at that 0? It's going to bounce off. So this is not the normal where we cut down and through. This, because it's got an even, I don't think I've explicitly said that out loud yet, because it's an even number of occurrences, then it's what we call a bounce root. And so the graph is going to come down And rather than like preparing to slice through, it's going to come down and begin to sort of feel like apprehensive and go, whoop, I'm going right back up, like a touchdown landing and head right back up. And then we know, of course, now that we can fit the end behavior, because with him bouncing back up like he needs to, then we know now that the graph will head back up and then finish his journey down like this. Any questions about that? So the expectation is, I haven't really made you, I can't make you do anything. I haven't really explicitly told you barked orders. You really need to start making your graphs. And again, they don't have to be artistically wonderful, but they're really important that we start actually sketching them out. So practice sketching those bounce routes and just making the graph generally look right. As you'll see, like when we put these into Desmos, we're not even close as far as like how high up this point is. According to my graph, that looks like it has a height of about 3. It's probably up somewhere around 38, 52. I don't even know. It's huge, but that's not what we're after again. That's just not important. So let's list our intervals and then we'll get on to the second example. So we can say that the negative intervals are here and here. And then the positive intervals are, of course, this one and this one. So let's go ahead and just knock out the negatives first. So we say that the function is negative over, so we say over this interval. So the word I should have been using from day one. And what is the first negative interval we see? It's coming in, always coming in hot from the left to the right. So zooming across, what's our first negative interval? Well played. That's exactly right. So the first stopping point occurs when I'm on the x-axis at -2. Then I hit the x-axis and go, whoop, I'm about to, something's going to happen right now. And then the graph emerges on the north side and we go, okay, we've switched over. So let's talk about our other negative interval and we'll come back to the greenies. What's our last one? 3 and infinity, right? And you don't have to write and, you could put commas or something like that. It doesn't matter. All right, and the positive intervals are 2 to 0, -2 to 0, of course. And what else? Nice. And I think this came up, but I have to ask it or I won't sleep well tonight. Why can those green ones not just be listed as one interval? Right. If you said to me that this graph is positive all the way from -2 to 3, I would call your bluff. I would say you're not right because that's not true. There's a point right, I'll put a big fat yellow arrow. There's a point right there where I could disprove you and say, no, it doesn't always have a positive value. That number breaks it. So good, good. All right, example 2, I'm so sorry in advance but I told them that I would do this. Example 2 is going to look, honestly, I don't think I would have ever spotted it. I'm not going to use other kids' names on my recording, but one particular student said, hey, that looks like a dragon. And I was like, it turned into a thing. I drew a dragon and I acted like a child and I drew like flames coming out of its mouth and we named it. You want to know his name? It was Hubert. His name's Hubert, the 5th degree polynomial function dragon monster. And it's pretty dope, honestly. In the end, I thought, gosh, Jeremy, you just recorded yourself acting like a 6-year-old. And then I thought, that was a good looking dragon. And then I forgot to hit share screen, so it didn't matter. So promised them I'd draw the dragon again. Annie. If you think I'm losing my mind, you might not be entirely wrong. Just FYI. There's our guy. This is the Hubert function, henceforth known as the Hubert, the Hubie. What do we do first? Absolutely. What is the greatest common factor? Negative. It's negative. 6 can go into all of them. Very good. So you kind of figure that if it goes into 6 and 48, that you're holding out hope that it works for 96, and it does. And how many x's can we yank? Yeah, so we're taking out negative and 6 and x to the third, and then we're going to rebuild, right? You never would skip the rebuilding step because you got to see what it is you're trying to factor. What's left over? X squared plus 8x plus 16, right? All right, so we made it through that step. And again, going back to a question from earlier, is there a trick to finding the GCF? Not really. It's just kind of roll up your sleeves and get in there and use your calculator to assist you when you're testing to see if things can divide by other things. What's left over is just a really basic quadratic trinomial. It's an old Algebra 1E level problem. So I have my GCF. And what does that factor down into? Yeah, it's a repeater. So there's where our multiplicity, well, not all of the multiplicity, but that's where some of the multiplicity comes from. So now that we've got that, remember, don't lose track of what we're doing here. We are setting this equal to 0. And then the fact that it equals 0 means we have to go through and figure out like how to make each of its component factors on their own equal 0, because that's the only way it would work. So we're going to go through now and find our zeros. So from this factor, what do we get? The red box. We do. We get x equals 0. And then just sort of little parenthetical comment, you want to say times 3. That's that multiplicity statement there. Yeah. And then we get a -4. But also notice that we get another -4. So we get x equals -4, but this one also has multiplicity, right, of 2. So, I'll tell you this, there's something that you don't really need to know this year, but I'm throwing it out because it's always nice when you get a chance. There's this thing called the fundamental theorem of algebra. It's really important to like really nerdy, smart people. And what it states is that you can tell how many zeros a function's going to have because it'll match the degree of the original problem. So like if we had to go back and look at the original, you would see that this was a 5th degree function, right? Like x to the 5. That tells you going in, I better get 5 answers out of this. That's called the fundamental theorem of algebra. And so when I look at my work, I can account for all 5 of those zeros. You always want to make sure that those match. And I can say 5 zeros because I got 0, 0, 0, -4, -4. So there's my 5 answers. They're not 5 unique answers. There's 2 unique answers with repetition, right? Okay, so let's make a sketch. And then now you get to learn about how odd multiplicities behave. Not all multiplicities are bounce roots. So let's make our axes. Trying to be mindful, I will at least, of the not wasting too much graph space. So I'm going to think about going more this way. Since I don't have any positive zeros, I don't see the sense in using a lot of x-axis on my paper. All right, so I'm going to label through my zeros. I'm going to go and now graph my first 0 occurs at -4. And then my second 0 occurs at 0. And it's hard to believe that the graph can have 5 answers when it only crosses or interacts with the x-axis twice, but it does. So let's do the one that we're familiar with first. Well, we need end behavior. I forgot. What is the end behavior? Definitely up down, because these two numbers circled in purple up here. The 5 tells me that they're different, and then the negative tells me to switch the default. So the default is low high. The flipper of that is up then down. So that's what we're expecting, not expecting. That's what the graph will do. So we know we have an up on the left and a down on the right. So just that information is enough for us to go, I got this. So you shouldn't be surprised by what the graph does at -4. You've seen this. This will be the third time now you've seen this exact particular multiplicity. So it's a bouncer, right? Because it's got that even multiplicity of 2, then we know that it's going to come down. And I can get rid of my little arrows now. So I can go down and I can say, I know how you interact with this portion of my graph. You're going to bounce off of the x-axis like this. This is one I don't think you've ever seen before. So now we have the question of what in the world is it going to do at 0 with an odd multiplicity? And what it does is, well, let me show you real quick, and then you can kind of help me come up with the words I'm looking for to describe its behavior. So it comes down and it's approaching, and you're thinking, oh, it's just going to cut through because it's odd. But before it cuts through, it does something that I think is kind of interesting. It flattens out a little bit. So odd multiplicities behave like this. It comes down and it flattens, curves, and then re-emerges on the other side. That's the way odd multiplicities behave. And I'm going to bring up Desmos here in a second to just show you sort of the accumulating effect of higher powers, but you'll see like they're all the same. Like they're just more like, what's the word I'm looking for? Exaggerated is the word I'm looking for. So if we want to complete the graph now, then that's pretty easy. We can just finish off this arm and yeah. So anyways, this was I better make his head a little bit taller. This was Hubert. And again, I'm not telling you who came up with this idea, but someone said that this looked like a dragon. And maybe it looks more like a dragon after I color in the intervals. So there's a positive interval. And there's a positive interval. And then, of course, we have, maybe it's because the tail is red. Would you guys get a dragon out of that? Can you see it? You seeing that, Lex? I'm not taking responsibility for this, although I am the person with the pen. I promised I would redraw Hubert, so here he comes. So this is Hubert. You guys are welcome to say hello to Hubert if you'd like, but you certainly don't have to. I think that's it. Do you like it? Lex? His name's Hubert. You want to compare him to the OG Hubert? You guys want to see OG? Or OH, I guess? Original Hubert. Let's see. Ready? Ready? Oh, that was anticlimactic. There he is. How did I do? Ready? Old Hubert? New Hubert. Old Hubert? Which one's better? You think OG Hubert's better? His flames look more dope, huh? Could I say they look more fire? Woo! All right. Anyway, sorry. No, I'm not sorry. That's fun. Dragons are fun. You did it? You drew the dragon in your notes? Yeah. I don't know. They said I should name him like Hubert version 2, but I think he can just be Hubert. They're like twins. So intervals are, how many intervals do you see? I also see 3. So let's go ahead and knock out the positive ones first. So this function is positive over, what's the first interval? Negative infinity up to -4. And then it ceases being positive because it touches that x-axis for that quick moment. And then it's positive again from -4 up until 0. And then it switches and stays forever negative over the interval from 0 to positive infinity. Good so far? So I wanted to show you something real quick because I left a little something out. So I told myself, don't forget this time. I wanted to show you some things on Desmos, just a couple real fast, I promise. So we kind of know already, I told you what multiplicity will do. So like if I gave you the graph of x to the third, you can now see what I mean, right? That the graph, so like here's the odd multiplicity of 1. So here's just like x to the 1. You see that's a that's a root that passes through at 0, but since it's a x to the 1, it just cuts right through, right? But now watch what happens if I add in x to the third. You see it's still crossing in the same point, but rather than just go straight through, it now does that thing I said. It flattens and then emerges. What do you think happens if I change it to like x to the fifth? I mean, there's no reason why you should be able to guess this, but watch the new graph, the red one. Do you see that it just got exaggerated? That effect of it flattening happens sooner and stays flat longer. And there's a reason for that. What do you think happens if I change it like x to the 13th? You get it, right? Look at that. That new graph is only, it looks horizontal. FYI, it never is flat, but we're limited by the resolution of what we can actually see. But you can see those different behaviors. That's pretty cool, right? So like x to the third is the black one, x to the fifth is the red one, and then x to the 11th is and we could keep going. And eventually you start pushing that flatness out towards -1 and 1 even closer. You can't get there, but you can get pretty close. So anyways, that's what I wanted you to see about odd multiplicities. They don't cut right through, they bend and then cut and then unbend on the other side. And then, of course, I wanted you to see also the even multiplicities, because this will come up on today's assignment. So you guys are all familiar with x squared. You know that he behaves like this. He's just a normal bounced root, right? What happens when I change it, do you suppose, to x to the fourth? You saw it on the screen before I deleted it. Did you? Maybe. It's pronounced, isn't it? And so there again is that idea that it's a bounce root, but the bounce takes long. I mean, it doesn't take longer. It feels like it takes longer because it flattens and it hangs down there longer before it touches again for liftoff. And as you would, of course, theorize, if I did something more extreme like x to the 10th, then you can really see that last graph really getting that flat effect on the bottom. And so you now know how multiplicity roots behave. The odd ones bend and cut, and the even ones bend and shoot back up or shoot back down. Got it? Let's knock out a couple more. F of x is the third one if you're keeping score. F of x equals 2x to the fifth plus 4x to the fourth minus 8x to the third minus 16x squared. What's the GCF? Absolutely, 2x squared. And I'll go ahead and just fill us back in. So we're left with x to the third plus 2x squared minus 4x minus 8, right? Got ourselves a grouping problem here. Let's draw that wall down the center. My wall's always kind of curvy, just the way I set these up. What is the greatest common factor of the left half? Absolutely. And what does that leave back? Yeah. And then, of course, you know by now, because I've said it 100 times, bring down the sign. And then what is the pull out from 4x and 8? 4 for sure. And what does that leave back behind? Yeah, no, it's so normal to want to say -2, and then we catch ourselves. And if you were to write -2, this is a really important learning process where you go, how come they don't match? And like, rather than just do the cheap move and just make them match, you go back and let yourself be a part of that and say, oh yeah, I pulled out a negative, so I have to switch the minus to a plus, right? Don't just make it happen. Make sure it happens for the right reasons. So my answer at this point in time is, here we go, greatest common factor times the common x plus 2 that you see in the line above times x squared minus 4. And are we content with that? You should not be. Like, we're completely not happy. There's a difference of squares, right? So I'm going to press on and I'm going to continue the hunt for zeros for answers. And I have, so 2x squared times x plus 2. And then when I factor down my difference of squares, it is x plus 2, x minus 2. And already you're probably comfortable enough that you can identify the number of zeros or the types that they are. So from my greatest common factor, what do I get? I get zero. I remember there's this, I'm sorry that we use the terms interchangeably. Uh, Zero, when we find a zero, that is a noun that describes the places where the graph crosses the x-axis, but zeros can occur at the number zero, which I know can be a bit vexing. So we get, and how much multiplicity is there? 2. So that's a times 2. That's going to be a bounce root. What else is interesting or significant? What do we get out of these that I'm underlining? They're both negative 2's. Yeah, so I can say I have a 0 at negative 2, but technically I have 2 of them because that 0 also has multiplicity. And then where's my final 0? Yeah. And again, just think about that fundamental theorem of algebra. You knew from the beginning of this problem that there were going to be 5 answers, right? There better be, because it said x to the 5th. And you can now go back and just kind of keep inventory and say, I found you all. 0, 0, -2, -2, 2. Boom, 5 answers. We'll make sure they're all accounted for. Now, when we make our axes to make our graph, again, just try to maybe be mindful of spacing or don't. Why do I care? We want to go from -2 to 2, so this one ought to be perfectly symmetric. So now you go through and you mark your zeros on your x-axis. So my first one, when I talk first, I mean like left to right, occurs at -2. My second one occurs at 0. And my last one occurs at +2. And behavior, going back and looking at from the very beginning, what did we think the end behavior will be? It'll be down up. Yeah, and it's not like an opinion or we hope it will be down up. It has to be. End behavior is non-negotiable. So it's going to be down over here on the left, and it'll be up over here on the right. So that's usually enough just to get your head around. So what is the behavior? What's happening at the 0, -2? Yeah, this one's a bouncer. The one I'm circling right now is a bouncer. And so now I understand that the bounce occurs on the bottom side. So I can kind of put in my bounce right here like this. Sometimes it's easier to fill these in and then go back and build the rest of the graph. And then what happens next up at 0? It bounces again. And so it's kind of interesting that like the only way this could happen now is for this bounce to also occur on the bottom side, right? Like there's no opportunity for the graph to have made his way above. You can't sneak past the math gods here. So like if you cross the x-axis, we would have known about it. And so we can fill in this part of the graph right here. And then of course, what happens at 2? This one else, yeah, it's a straight old school straight through, like no bend or anything like that. That's an old school, just a crosser. So it's going to come down and just right through. No, again, no whoopsie-doo, floopity-doo stuff. It's just straight through. So to complete the graph, then you can do this. And I'm sorry, my arms probably shouldn't be going straight, but you get the idea. All right, how many intervals do you see? I also see 4. I see a negative here. I see a negative here. And I see a negative here. And then I only see one positive interval, and that's this guy over here. So, right. So let's list them out, make it official. We can say negative over, and we're going to have 3 of these. What's the first one? Next one. You guys are really amazing. You've handled this all very well. Stuff like this as a teacher, I worried would be like, we're starting to get into some weird. You guys are just really good. Good job. And then the last one is 0 to what, 2? Okay. And then my positive interval, there's one of him, and he occurs over the interval from 2 to infinity. That's that. All right, one more example. And I know you probably feel like, hey, we're good to go. I feel like when I wrote these, everyone had a purpose. So let's make this official. One more. What's the end behavior going to be? You know already. It is going to be up, up. Very good. You've mastered the end behavior up there. Good job. GCF is x to the fifth. Very good. You can call it x5 if you really want to. It sounds like a fighter jet. The X5 fighter jet. What does that leave behind? Beautiful. And that's pretty standard grouping, I would think, at this point in time. So out of the first half of the wall, we pull A, and that's squared, leaving behind.
No.
X plus 1. You okay there, Annie?
Yeah, I accidentally put 5.
Feel better?
Yeah.
All right, good. Then we're going to drop our sign, and that's a negative or a minus, call it whatever you want to, kind of one and the same. And then pull out a 9, and that leaves behind. Yeah, X, change the sign 1, right? You got to pull that negative, you got to change the sign. So this time I'm going to skip a step, and if you're not comfortable with it, then I'll go back and unskip the step because I don't want you to feel like that was mean. But at this point, I'm going to just finish it off. So I'm going to bring down my GCF, X to the fifth. I'm going to bring down my commonality of X plus 1. And then while I'm here, I'm just going to factor the difference of squares. It's kind of to the point where we see it coming down the pike, like you know it's going to be there. So just knock it out while you're there. I remember now why I wanted to do this example. It wasn't just because it fit nicely on my note card. I remember having written the first 3, I thought to myself, like, I don't want them to get the impression that you're missing something if it's not too exciting. Like, I just wanted you to know that sometimes you can just get a lot of different routes. So, yeah. Where? Yeah, but that's a difference of squares, which, so that was kind of what I was worried about. I usually am better about showing my work than that, but yeah, that's why it splits that way. Y'all better? Okay. You scared me because I do make mistakes, more so every year. I make more than the year before. So how many zeros, how many unique zeros do you see? Like overall, we know there's going to be 8 because that's what the math god said. The fundamental theorem of algebra said x to the 8th, there's going to be 8 answers. How many unique answers will we have? We'll have 4. So let's get to it. The first one comes from right here, and his name is 0. And how many of him will there be? So that one gets a little x5, right? That's a times 5 multiplicity. And then next up, we get just some singletons, right? These are not going to be benders. These aren't going to be bouncers. These are just normal crossers. So we also get x equals -1. We get x equals -3. And we get x equals +3. All right, so let's take a peek at the graph. And the multiplicity will factor in at the origin, at 0, it's going to have some behavior, some bendy behavior. This one goes from -3 to 3. So again, I'm going to just try to keep it symmetric here. And my first 0, if I'm coming in from the left to the right, my first 0 occurs at -3. So I'll stick a 0 there at -3. My next 0 occurs at -1, and that's probably right about there. My next 0 occurs at 0. That's the exciting one. And then my final 0 occurs at 3. So way over here somewhere. Something like that. All right, let's get to it. What is the end behavior? I think you told me earlier already. It's up, up, right? Because the 8 on the exponent means they're the same, and the positive number in front means that sameness is upness. So up, up. So my arms will end over here. and over here. It's good to know. So what is the behavior at -3? That's this first 0 right here. What is the behavior going to be? How will the graph interact with that point? Yeah, old school, straight through. So we can just dipsy-do down and just cut right through the graph at that point. No bending, no bouncing, just old school. What is the graph's behavior at the next 0, -1? That's not the flat one. I'm so sorry. I didn't realize that. Just give me one more minute, guys. I'm so sorry. And that one's going to come up like this. That's a normal crosser. But this is the one. I can't believe I wasn't watching the clock. I'm getting old or something. So this one is going to, this has a multiplicity of 5, right? So this one is going to come down like this, and it's going to flatten a lot like this, and then it's going to reemerge like that. You see how unique that behavior is, and that's because of the odd multiplicity. And then, of course, since it ends up, it's going to dipsy-do down, come back up. Sorry, that's a really bad graph, but that's that, guys. So remember, tomorrow, work day, be on your super best, perfect behavior. And I look forward to looking at an awesome sub report on Friday. And if you need help, I'll be here for Friday school. You like it?